Greetings! In this video, we'll explore how to create a basic program in WebGPU by using UWAL, a simple JavaScript library aimed to abstract some tedious setups when working with WebGPU APIs. One of the things I like the most in WebGL are tunnels. You can search for them on shadertoy.com and be amazed by some beautiful animations made by using just fragment shaders. To me, creating a tunnel with some rendering library is like making a to-do app in JavaScript with any of the most popular front-end framework at the moment. It's a perfect showcase of what can be easily achieved with right abstractions and extremely hard or nearly impossible to accomplish with Canvas 2D APIs and plain CSS. So let's do just that. Let's create a simple, animated tunnel with UWAL and WebGPU. Let's start by scaffolding an empty project using vite and bun. We open a terminal window and run bun create vite at latest. Call it UWAL basic program, and to keep things simple, we choose vanilla and JavaScript. Let's then cd into the folder and install required dependencies by running bun install. We then add UWAL with bun add UWAL command, open Visual Studio Code, and start the dev server by running bun dev. Let's delete some files we won't need, optionally add VS Code settings, and edit the git ignore list. In our HTML file, we can then change the title, add some initial styling, and create a canvas element, the heart of this application. Now, the main JavaScript file can be cleaned up from vite's boilerplate code, and we can start programming by importing the UWAL library and getting a reference to our canvas. Usually when initializing the rendering pipeline, it's better to opt for a safer option, that being wrap the renderer instantiation in a try-catch block and notify your users whether WebGPU is not supported by their browsers. It's also considered a good practice to label pipelines, buffers, textures, etc., but since this is just a demo, and we want to keep things simple, let's rewrite that in one line and assume no errors will be thrown in this stage. We'll need a window resize event callback where we update the canvas size to match the entire viewport, attach a listener to handle this event, and call resize function immediately to set the initial canvas size on page load. Finally, we can create a new render pipeline by calling renderer create pipeline. Open a browser that supports WebGPU and get a very exciting blank screen. Awesome! Great job! Now let's recreate a basic shader from ShaderToy when creating a new project. This will be our starting point, just like on the website. We import it as a raw string for a file we'll create in a bit and call it tunnel. We'll also need some base shaders provided by UWAL, so let's import them as well. Now we extend our pipeline by creating a shader module and passing to it the quad shader, which is responsible for creating two triangles and fitting them to cover the entire canvas area in our tunnel shader. We'll be using a uniform called input to pass some values from JavaScript to the GPU. So let's create a uniform buffer to do just that. Create uniform buffer method is handy because it will return the GPU buffer and also the view of the input struct, taking care of data memory layout, computing sizes and offsets, and creating correct typed arrays for each member of our input uniform, all under the hood thanks to the awesome WGSL reflect library. We can now use our newly created buffer in a bind group. So we create a new bind group entry from our uniform buffer, and we create a new bind group with this entry and set it to be used by the render pipeline. Sweet! Finally, we can set up our render loop. Let's create a function called render that will be accepting the current timestamp from request animation frame and use that to get the current time of the program in seconds. We need to update our uniform buffer with this value, and we do that by calling rendererWriteBuffer, which accepts the buffer itself as the first argument and the data to write as the second. You may wonder why the time member of the input uniform is being used as an array here. Good question. That's because the WebGPU device queue_writeBuffer method requires for the data value to be either an array buffer, an array buffer view, or a shared array buffer. For this reason, and to keep things simple, every entry returned from create uniform buffer is an array buffer view. So in this case, Time is a float 32 array with a single element at index 0. As we'll see later, vector 2 will have 2 elements and so on up to matrix 4 by 4 with 16 elements. In this way, we can separately update each member of the uniform and don't worry about offsets or update them all together by passing time.buffer, as we'll see later. We can now call renderer.render to actually draw something on the screen, request the next animation frame, and call it once again outside the function to create the render loop. Now, to the shader. Let's actually create the tunnel wixel shader file. We start by describing the input struct we're using in JavaScript and the bind group used to communicate with the GPU. Next, we create a vertex shader whose sole job is to return the coordinates of the current vertex index derived from a function we included earlier in shaders.quad file. Finally, in the fragment shader function, which accepts the current pixel coordinates as an input parameter, we can recreate the same base gradient from shader toy. Let's temporarily hardcode the width and height of the current screen size, as this code is only to verify that the pipeline is working. We'll see later how to pass the actual screen resolution to the shader. We can compute the color gradient by adding together the current program time in seconds, swizzled pixel coordinates, and a constant vector. Furthermore, we then tweak this value a bit by levering the cosine function and return the final color as a vector with 4 elements. If everything was done correctly, we're now able to observe the base shader from Shader Toy in our browser. We will need some texture to be used as walls for our tunnel, so let's add and import that into the project. We will also need some texture constants later on, so let's import those as well. In the shader, we will need to do some math based on our canvas size. So let's refactor the resize event handler a bit so we can reference the resolution buffer created for us by UWAL and add that to our bind group entries. We also need to add the resolution shader to our pipeline to actually use this binding, which will be always set at index 0. We create a new image object, set its source attribute, and handle the loading event. When the image is loaded, we create a new texture helper from UWAL's class and pass to it our renderer instance. So then bitmaps can be dynamically generated on the GPU. We create a new texture from just loaded image by calling texture.copyImage to texture. To sampler the texture in the fragment shader, a new sampler has to be created. We use address.repeat constant to flag that this texture will repeat infinitely along the axis. Finally, we create a new bind group by calling renderer add bind groups so that the previous one won't be overwritten and set its group ID to 1, since 0 is already in use. This comes with a benefit that we can keep the data used to read the texture and the uniform in 2 separate bind groups to split the logic a bit. Last thing left to do is to move the first render call into this function, so we can start rendering once we have all data fully loaded. In the fragment shader, let's change our input binding index to 1, because as I mentioned earlier, resolution uniform is going to be always 0, and add our new bind group bindings, the texture and the sampler. We won't be using the input uniform at the moment, but we need to keep it here so that WebGPU won't throw warnings on us and keep rendering the scene. Let's keep color manipulations and compute the current pixel position from input coordinates and the canvas resolution. Finally, we can sample our texture by calling textureSampleWixel function and pass to it the required data. Seems like it's working. Very good. There's one improvement, though, we can do. I mentioned that having 2 bind groups comes with some benefits, and it's a bit easier to set up. But in reality, most devices can have only 4 bind groups but hundreds or even thousands of bindings in one group. So in order to save on groups amount, let's use just one and bind to it our buffers, texture and sampler. The change is very easy. We remove our first bind group and add its bindings to the second one. Again, the important thing is that the resolution buffer ends up at index 0. This is now our first and only bind group, so we can call set instead of add since no other group will be overwritten anyway, and remove the group index, which, as you may have guessed, defaults to 0. Last thing left to do here is to update group and binding indices in the shader, and we're good to go. Still working. Cool. Let's make things moving, shall we? Let's start with a small trick to never remember the pi value ever again. Next, we compute the angle from the current pixel to the center of the screen and the radius of our tunnel. We override the vector UV to sample our texture and to darken the tunnel in the middle at some distance. We update our sampling, this time using the newly created UV coordinates, and get the vector 3 color out of it. Finally, we return this color multiplied by the radius with an alpha value of 1. Easy as that. With just a few lines changed, we finally have something resembling a tunnel. Cool. But if you say that everything up to now could be achieved with an image loaded in one line of HTML and some CSS, you'd be totally right. Let's fix this by adding some clockwise camera rotation. We can now remove color manipulations at the beginning of the fragment shader, since we'll be using input time uniform to update those position coordinates. By leveraging cosine and sine functions, we can create an illusion of camera movement. But let's also clamp those values a bit, so the center of the tunnel won't end up right at the borders of the screen. By using the time uniform once again, this time when calculating the u-coordinate, we can fake the movement along the z-axis into the depth of the tunnel. Pretty cool stuff. There's one issue though. Our texture sampling is not perfect because it causes this weird vertical artifacts related to MIP mapping and discontinuities in the texture coordinates, especially visible when there is some camera movement like in our shader. Luckily, there's an easy fix from the man himself, Inigo Quiles. We compute UV derivatives by hand instead of letting the GPU do this automatically for us. Because of this approach, we now have to use a different Wigzel function, texture sample grad, which besides the already known parameters, also requires partial derivatives of UV coordinates. That's it. We keep everything as is for now, and we get a nice camera pan animation inside the tunnel without sampling artifacts. Not bad. There's no way CSS can do that. This part is optional, so it's up to you if you want to skip it, but I think it might help to achieve some nice look and feel for our tunnel. We start by creating a new WGSL file called vignette, where we'll use some pixel manipulation to tweak our tunnel appearance. Let's declare a new function random that, given a vec2 value in input, will return a pseudo-random float number. The approach used here is very simple and naive, but it will get the job done for a slight effect like the one we need in this algorithm. Next, another function blend will nicely mix two color values to produce one in output. And then, there's a vignette function that will take an input the fragment color and its pixel coordinates to mix them once again. This time using a black color with the actual pixel value and the smooth step function. Now we can mix this smooth color value with the blended one and apply some slight randomness to it. That's it. Our vignette effect is ready. Back in our tunnel shader, we just call our new vignette function with a proper UV value and return the output produced by it as our final fragment color. Let's not forget to import and add the vignette shader to our render pipeline, and we're good to go. Another cool improvement is color grading applied by the matrix formula, which I discovered recently thanks again to Inigo Quiles. First, let's define some red and blue constants at the top of our shader. Now, right before calling the vignette function, we can do some color manipulations using these values to produce a darker, more green color, just like with a filter applied in Matrix films. I'll leave a comment with a link to Inigo's YouTube short, so you can check how it works by yourself. One last trick, if we want, we can easily replace or even blend our cylindrical tunnel with a squarish one. Let's create an overridable variable to play around with this. We'll be able to redefine its value in JavaScript even after the shader module has been created. However, I won't go that deep in this video. If we want our tunnel to look like a square, we need to recompute the radius value. By elevating the pixel position to the power of 8, we can then call the pow function with the sum of x and y coordinates, this time with the exponent of 1/8, which is equal to 0.125. And by the way, if you're wondering why we compute the power function for the position coordinates by hand and didn't call the pow function with the position vector and 8 as an exponent, it's because this operation, with a such high exponent, might produce some unexpected behavior when done on the GPU. I learned it the hard way. This already looks pretty darn cool, but let's improve it just a bit by adding some user interactions, shall we? First thing first, let's create a target array so we can save the current mouse position and a clamp function to easily normalize this value. Next, we create a mouse movement handler to save the current mouse position in the target array, but before we do that, we normalize it to go from -0.5 to +0.5. Actually, not quite. Let's tweak these values a bit so the center of the tunnel will never reach screen borders, even when the mouse is at the end of the canvas area, just like in our shader. We add a new event listener and a new entry in our input struct. Now we pass our mouse coordinates to the shader on every frame. This is going to be a vec2 and wixel, so an array with 2 elements in JavaScript. With a little bit of math, we can make the camera movement much smoother. Let's multiply these values by some small number and update the whole uniform buffer altogether with time.buffer, as mentioned earlier. Of course, since every entry in a struct created with createUniformBuffer is just a different view of the same array buffer, we can also use mouse.buffer to achieve the same result. Nonetheless, back in our shader, we switch back to a cylindrical tunnel and add the mouse member. To check the result, let's comment out the automatic animation. We'll still need it later, and use our new mouse coordinates. Not bad at all. As the very last thing I'd like to do here is to resume the automatic animation if user's mouse ends up outside the canvas area. To achieve this, let's create 2 new variables, one to save the rendering time and one to detect if the mouse is inside or outside the screen. We add 2 more listeners to toggle this value and a new float variable in our input struct. We can now use movement to easily mix between tunnels positions in the main shader, just like we did before to mix output colors. It's going to increase or decrease its value from 0 to 1 based on the hover variable. We can also manipulate the last time value a bit more to smoothly move the camera from the current position to look at our mouse and back to the position computed with current time, sine and cosine functions when the mouse leaves the canvas area. And let's not forget to increase the last time value at each frame. Finally, in our shader, we can add the movement entry and mix 2 position vectors based on its value. Let's also slow down the automatic animation, so everything will look more chill. That's looking pretty nice, huh? Hopefully, this video was a good explanation of what can be achieved with UWAL in just 90 lines of JavaScript code that could rapidly expand to a couple of hundreds when using plain WebGPU APIs. We learned how to create a render pipeline, a GPU texture from an image file, set up and use bind groups, and update buffers on render time. These sorts of animations can be easily customized and integrated in a landing page so that anyone can play around with them while reading the heading of your website. Feel free to try UWAL by yourself and fork this basic program on GitHub. I'll leave both links in the description of this video so you can check the source code and the live version. Thanks for watching. Cheers!